Most people find the explanation of Schuler errors using the moving diagram a little complicated, and you are not expected to be able to remember it in detail. This is why the pendulum analogy is popular. When we discussed platform stabilization in an earlier lesson, we said that the V/R feedback loop could be likened to a large pendulum with a length equal to the Earth's radius, with the platform bolted on at right angles. The bob of the pendulum remains at the centre of the Earth. Then, as the aircraft travels, the circular motion of the rigid part of the pendulum keeps the platform level. Continuing with this analogy to explain Schuler's errors, if the platform is not level at the start, then this is like starting with the pendulum off-centre. When the pendulum is released, it will swing with a period of 84.4 minutes. As the aircraft travels round the Earth, the Schuler loop will still try to keep the platform levelled with the local horizontal, which is what it's designed to do, but it will have an unwanted Schuler oscillation superimposed onto it. Let's now see which of our errors will give a Schuler pattern. Firstly, we'll remind ourselves of the full list. Then we'll look at the feedback loop to see what caused the platform tilt oscillation error. The problem was caused by a feedback of false velocity through the V/R loop. So if any of the input errors gives us a false velocity, we will get a Schuler oscillation. Let's look at what could cause a velocity error. As we have seen, the platform might not be level. Secondly, there might be an accelerometer bias. And finally, there might be first-stage integrator error. These are the only three. The combination of contributions from all three gives us our Schuler error. These errors are also known as bounded errors because they do not increase with time. We'll now go on to unbounded errors. There are other errors, and they do not follow this sinusoidal pattern. Instead, they get worse with time. The second-stage integrator is a good example. It is outside the V/R feedback loop. Suppose an aircraft were to fly at exactly 400 knots for an hour, but the second-stage integrator were to output 401 nautical miles distance gone. Then, after 2 hours, the aircraft would have actually flown 800 nautical miles. But the integrator would have output 802. After 3 hours, the true distance is 1200 nautical miles. But the integrator would have output 1203, and so on. This kind of error is a different pattern. It is called a ramp or unbounded error. Another obvious example of an unbounded error is initial azimuth misalignment. Clearly, the further you go, the worse the cross-track error gets. There are 4 sources of unbounded error, and they combine to form a ramp pattern. In practice, Schuler errors and ramp errors occur at the same time. So we have a ramp pattern like this, with a Schuler ripple superimposed on top of it, so that the complete error pattern looks like this. Here is a summary of INS errors. Bounded errors oscillate about a mean value and have a sinusoidal form with a period of 84.4 minutes. They do not increase with time. They consist of platform tilt, accelerometer bias, and first-stage integrator error. Unbounded errors increase with time. Their form is a ramp. They consist of initial heading misalignment, levelling gyro topple, azimuth gyro drift, and second-stage integrator error. Unlike our earlier diagrams, which were idealized, this is an actual plot of INS against GPS on a test flight. The pattern can be clearly seen. There is a basic ramp increasing at approximately 1 nautical mile per hour, with a 1-mile Schuler oscillation superimposed on it. How can we correct or remove these errors? The answer is that we can't. All of these bounded and unbounded errors result from limitations in the accuracy of the components of the INS. They arise from the accelerometers, the integrators and the gyros. They can all be considered to be a more sophisticated form of instrument error. There is nothing that can be done about them within the INS itself, except to improve engineering standards. And this did happen with the evolution of better and better manufacturing techniques during the 70s and 80s. Even with these errors, the general accuracy of an INS is good compared with previous systems. This plot shows only an 8-mile error after 9 hours of flight. For a standalone system, this is very good. However, from the 90s onwards, 2 developments occurred. One was the introduction of the ring laser gyro to replace the old tune rotor gyros. Systems using these new gyros were usually called inertial reference systems. We shall cover the ring laser gyro and the IRS in more detail in the next lessons. The other was the idea of using the INS or IRS as only one component of a multi-sensor system, and to have a method of extracting the most probable position from a combination of all of the inputs. This multi-sensor system is part of the Flight Management System, or FMS for short. And the method of establishing the most probable position from a variety of inputs is called Kalman filtering. The later generation of inertial systems, which are generally known as Inertial Reference Systems, or IRS, are usually part of an Integrated Flight Management System, FMS. In the Flight Management Computer, or FMC, there are usually 2 or 3 IRSs, each generating its own present position. These IRS positions are compared with independent sources, such as Global Positioning System or GPS, and computer-generated calculation of crosscut positions, which have been obtained from ground-based radio beacons called distance measuring equipment. The computer automatically selects those DME stations along the route which will give the best crosscut, and calculates an independent new position several times a minute. The crosscut positions are called DME positions. Not all inputs are always available. DME is a line of sight system, so it can be blocked by hills or the curvature of the Earth. GPS can have blank spots. A process known as Kalman filtering produces a statistically most probable position, known as the FMC position. From this FMC statistical best estimator position, it is possible for the FMC to establish an error trend over a period of time, and to build mathematical models of both the Schuler and the unbounded error propagation pattern. This is then used in the computation of future computer-generated positions. Kalman filtering is complicated and does not lend itself to broad simplifications. However, it is important to realize that the FMC position is not the average of the IRS and DME or GPS position, but is computer-generated using a sophisticated statistical algorithm. Let's summarize this lesson. We reminded ourselves of the basic data flow diagram. Then we identified the sources of error. We looked at sources of error within the V over R loop. And we saw why Schuler oscillations happen. We reminded ourselves of the pendulum analogy for normal platform stabilization, and then extended it to include the platform not being level at the start. The Schuler period is always 84.4 minutes. and the maximum displacement at the successive 42.2 minute points is always the same. We then said that there were other errors that don't fit this pattern, and that these are known as unbounded errors. This is the summary of errors, which you must remember. They give an error propagation pattern like this. On a standalone INS, these errors cannot be removed. They can be minimized by the use of more accurate components and expensive engineering techniques. However, the later generations of inertial systems are only one of several sources of position in a flight management system. And a statistically most probable position is computer-generated by the Kalman filter in the FMS. However, the FMC position is not the average. This concludes our study of INS. The next lesson goes to look at its successor, the IRS.